Hi, welcome to 7.4. We're going to talk about different ways of seeing the quadratic function. So here are three functions, and a little spoiler, they are all the same function. But I have f of x, g of x, and h of x. And let's go through each one and see what bits of information can we get from each one. So starting with blue, let's go to h of x, because we've been just talking about functions that look like h of x. In h of x, we see that this looks like a transformation function, where we have a variable inside with the operation happening just outside of it in parentheses, and then it's being multiplied and subtracted. So from this information, we can find out that we have our a, h, and k. So starting first with the h and k, with the -1 and -12, what this tells us are our shifts. And with the shifts, what it does shift when we've been graphing it is our starting point, like our point of reference. And for quadratics, that is our vertex. It shifts our vertex to wherever the points are, wherever h and k are. So this is telling us I want to shift -1 because h is -1, and I want to shift down to 12 because k is -12. As a result, our vertex is now at hk, or in this case, it'll be -1, -12. That is information given to us with this function, which is very important in order to graph what it looks like. Next up, we have this 3 as well. The 3 is our a value, and what this tells us is there's a vertical stretch, or a greater rate of change. That is what this information is telling us. So this formula of writing the function tells us this information, the vertex and the vertical stretch that's happening to it. Moving on from right to left, we have g of x. This function we've been seeing a lot. We've seen it even last year as well. We have a basic quadratic, x squared, x, and a constant. So let's see, what do we know from this information? What's easy to find here? And what's easy to find is this right here, our y-intercept. So in this way of writing the formula, when we set x equal to 0 to find the y-intercept, this whole front section becomes 0, because anything times 0 becomes 0. So you end up with g of 0 is equal to 0 plus 0 minus 9, or -9. So your y-intercept is at -9 or 0, -9. So this way of writing the formula tells us my y-intercept. Finally, at the very last form, we have it all factored out. And when we have it factored like this, it's very easy to solve for when the whole function equals 0. Because when we set values equal to 0 when they're factored, anything times 0, like we mentioned before, is equal to 0. So we set 0 equal to every single factored bit. 0 equals x minus 1, 0 equals x plus 3. This one does not work. We get x equals 1, x equals -3. So we're finding the x values when the function equals 0, or in other words, we want to find the x-intercepts at those values, or at 1, 0, -3, 0. So let me just recap what we found. H of x tells us our vertex and our vertical stretches. G of x tells us the y-intercept, and f of x tells us the x-intercepts. Another thing we can notice is that I have a right here. I have 3. Where else do I see 3? I see 3 right here and 3 right here. Those are all the same a's. So that was a quick little recap of everything that we see about these functions. But let's now prove that they are equal. So the hardest one that like h of x seems a bit weird. We know how to factor a quadratic out to get f of x. We know how to FOIL and get it back to standard form. But h of x is a bit confusing. So let's use h of x. And let's solve it out. Ignore this. But when I have h of x right here, let's evaluate it out. So using PEMDAS, parentheses first, I can't do anything here. So I then must use exponents. So I squared it inside. X plus 1 times x plus 1. We FOIL it out to get x squared plus 1x plus 1x plus 1. 3 times x squared plus 2x plus 1. 3x squared plus 6x plus 3. And finally, we get 3x squared plus 6x minus 9, which if we double check is equivalent. So to go from f of x to g of x and from h of x to g of x, we can just FOIL it out. We can FOIL it out and get the standard function. So that shows us that these functions are all equivalent. Let me just tuck this away. Do another copy as well. So these functions are all equivalent. But why are we writing in different forms like this? That's because we get so much information about this function. Instead of having to graph it out, look at Desmos, and see all these values, we could actually find all these values just from different ways of writing the function. Where if I write it in standard form, I get the y-intercept very easily. If I write it in factored form, I get the x-intercept very easily. And if I write it out in this form, I get the vertex and like transformations very easily. So let's define this. Let's write this out in the clear way like that. So starting from the most standard, we have standard form, which is f of x is equal to ax squared plus bx plus c. And what do we get from this? We get our y-intercept very easily. Y-intercept. That's very easy to find. It's also very easy to get to and factor it out. The next one that we've learned before is the one on the left, where it is a factored form. So we factored out standard form to get our function is equal to a times x minus p, x minus q, where p and q are our zeros. They're x-intercepts. So this factored form tells us x-intercepts very easily. And finally, we have vertex form, which is just like the transformation forms that we've been using before. We have a times x minus h squared plus k. This tells us our shifts, or our vertex from our shifts, and transformations very easily. And we want to memorize this, like where we get all this information from. And we see something very simple across these. We see I have A, I have A, I have A. These are all, once again, the same A. A's are the same. Let's even write this in the Galaxy font. A's are the same. All these A values are the same. We have 3, 3, 3. They're all the same A, which will be important to go from standard to vertex. So let's now tack on one more thing and let's do one example problem to see this application. So we get from vertex form to standard form by FOILing out, which we did right here. We go from standard form to factored form by factoring. We go from factored form to standard form by distributing out. we don't need to go from factor to vertex because we have standard form as a bridge. So that's why I wrote it in the middle. Standard form is the bridge that connects all three forms. Okay, so resuming from where I left off, we want to get back to vertex form somehow from standard form. And we can see right away, we do have A. So to get from vertex to standard form, we can just identify A from standard form. We use the same A. Oh, why is it so? What happened to this? Okay, so that's a bit weird. Let me change it like that. We use the same A. But next up, we need a vertex. So let's go through how we find the vertex for each one. So starting with vertex form, vertex is equal to HK. Nice and simple, that's a vertex. For factored form, we'll pause on standard form for a second. For factored form, we see that we have 2 points already. And the thing is with x squared, the quadratic, is that it is symmetrical. No matter how up I go, it'll always be symmetrical. And even if I move it around somewhere, minus h, slider for that. No matter where I move it, it'll always be symmetrical. Plus k, slider. It'll always be symmetrical. So therefore, since it is symmetrical, and I have 2 points, it must be symmetrical at my midpoint. So to get my x value for this, to get vertex, your x for your vertex is equal to p plus q divided by 2. Where I just average out my 2 points that I get, my 2 x-intercepts, and that's your x value for your vertex. And to find the y value, y is equal to f of x, this x value. So you find the y value from here, and then you get that vertex. So your vertex is equal to p plus q over 2, and f of p plus q over 2. So find your x value first, and then plug it into the function to get your vertex. And the same logic applies for standard form. Where to find the vertex, we want to first find it. And this formula, I'll just give it to you, and we'll explain it more in the future. But x is equal to negative b over 2a. So you find your x value using this, and you find your y value by plugging that into here. That's my x value. So your vertex is negative b over 2a, f of negative b over 2a. Now let's test this real quick, because my vertex is at negative 1, negative 12. And with this function right here, let's see what happens when I test this value. So x equals negative b over 2a. X is equal to negative 6 over 2 times 3, or negative 6 over 6 to give me negative 1. I now want to find f of negative 1. So plugging it into here, 3 negative 1 squared plus 6 negative 1 minus 9. 3 times 1 plus negative 6 minus 9. 3 minus 6 minus 9 to give me negative 12. So my vertex is at negative 1, negative 12, which is exactly what I found before. Right now, you could pause. You could try out doing it for your vertex form. Not vertex form, by factored form. Where we have positive 1 and negative 3 as your p and q. So you use that, plug it in, get your x value, and use that x value to plug it into the function again to get your y value. You should get the same point for your vertex. So let's sum it all together with an example function. So let's get this function f of x is equal to x squared minus 8x plus 15. And I'm going to lay out exactly how we should solve it out. So to solve a problem like this out, where you want to find all the information, all the key values. Actually, I forgot one thing real quick. I mentioned symmetry, but I never did something with the symmetry. Your symmetry, where you find the axis of symmetry, your axis of symmetry is at your vertex. X equals your vertex. Vertex is x value. Because your vertex is where we turn, so that's where you're symmetrical. So your x is equal to -1 in this case. And we say x equals because that gives us, you see right here, x equals h. When we move around, that's where my symmetry is. It'll always go through my vertex. So my x is equal to my h value, or my vertex is x value. And now we're all set. With one exception of finding range, which we'll do with this big example. So let's have f of x is equal to x squared minus 8x plus 15. And to solve this out, we have a bunch of steps that I'm going to write in this way. 20. First off, we want to find the vertex. Next up, what we want to do is we want to find the x-intercepts. Find the y-intercepts. Actually, with the vertex, we also find the axis of symmetry. Find x-intercepts, find the y-intercepts. You want to find the other two forms. Actually, we could graph the function. Find the range, which we'll see a trick after we graph the function. But it's always good to double check with the function. And you want to find the other two forms. So there's a lot to find out with this problem, because we're kind of summarizing everything we know about functions, about quadratics. So let's start with the vertex. With this form, we see that I need to use for vertex, I need to find out when x is equal to -b over 2a. So my vertex x equals -8 over 2 times 1. 8 over 2 equals 4. Now I find f of 4 to get 4 squared minus 8, 4 plus 15. 16 minus 32 plus 15 to get -1. My vertex is at 4, -1. Vertex. Before everyone, I'm going to kind of pause and let you guys try to pause the video, work through the next step with a little pointer. So now we want to find the axis of symmetry. Look back at our notes and see how we can find the axis of symmetry. So axis of symmetry is from our vertex. So we want to find the axis of symmetry. We just find the x value of vertex, which is +4. So that is my axis of symmetry at x equals 4. Next up, we want to find the x-intercepts. So look back at our function types and see which one we need to turn it to get our x-intercepts. So you should have seen that x-intercepts are found in factored form. So let's now turn this into factored form by factoring it. So f of x, we have x squared minus 8x plus 15. So I see what multiplies to 1 times 15, because AC method, and adds up to negative 8. You have negative 5 and negative 3. X squared minus 5x minus 3x plus 15. Continue factoring to get x minus 5, minus 3, x minus 5, x minus 3 times x minus 5 as factored form. We found factored form. Factored form. This will come in handy later because we don't want to repeat work every single time. With factored form, we then set it equal to 0, and x minus 3 equals 0, x minus 5 equals 0, to get x equals 3, x equals 5 as your x-intercepts. And now let's find the y-intercepts. So once again, look back at your forms and see which one helps us find the y-intercept the easiest. So to find y-intercept, all we need to do is pick a form and set it the x value equals 0. But if you have the standard form, we just look at the c value and see what c is. So I have standard form right here. So to find the y-intercept, I see y-intercept c equals positive 15. So my y-intercept is at 15, or 0, 15 for my coordinates. Now let's look at graphing the function. So look at all our points and see, do we have enough information to graph our function on our graph? And a reminder what we said last topic, you only need 3 points to graph a curve. So on our paper, we should have been able to draw xy axis. And I always like to start with the vertex because that's my midpoint. So I have 4, negative 1. 1, 2, 3, 4, 1. My vertex right here. The other points that I have are my x-intercepts, 3 and 5. So at x equals 3 and x equals 5, I have intercepts at when y equals 0. Another point that I have is y-intercept at positive 15, which kind of goes beyond. It'll probably be like up here somewhere. You can graph it if your graph fits it, but we already have 3 points, so we don't need it. Now I can just go and draw my little curve. Mine's a bit wonky, but we have a quadratic with 3 points. Make sure you, actually I can move mine. Make sure you touch all 3 points. There. So there's my graph. You may be asked to label some points, so make sure you label the points if you're asked to. Next up, we want to find our range. So looking at our graph, try to find the range, but also see, is there a way we could find the range using some of our points here, some of our values that we found. So domain, I didn't ask us to find domain because it's kind of arbitrary, but for all quadratic functions, it will always be from negative infinity to positive infinity, because we'll always have arrows in 2 directions. Negative infinity, positive infinity. My range from the graph, we said I'm starting from negative 1 and I'm going to infinity. And my range is directly tied to my vertex, because my vertex will always be a point at which I turn, either my minimum or my maximum. So when you look for your range, find your vertex, see where your y value is, but also see, am I reflecting? Because we're tying into previous knowledge. So I found my vertex, and how do I know if I'm flipped or not? I see my a value. My a value here is positive 1. Since a is positive, I know my range, my y, must be greater than or equal to my k value. If a is negative, my range must be less than or equal to my k value, because it must be flipped and k is my maximum. You could test this out in Desmos and try out different a values and see what happens to my function. And now finally, we need to find my other 2 forms. So my other 2 forms, first up, I have my factored form. which we found earlier when we found our y-intercept, our x-intercepts. So my factored form is f of x is equal to x minus 3 and x minus 5. My vertex form, what did we need? We need my vertex and my a value. F of x is equal to 1 x minus 4 squared minus 1. Because my vertex is positive 4, negative 1, and my a is positive 1. You don't need this a value there because multiply by 1 doesn't really do anything. So both answers are acceptable. So we did everything, tying everything together. And doing it this way, you don't need to do it in this order, because you see that we could have found our y-intercept before our x-intercept because we had standard form already. You could even find range before graphing it. But I find this the most practical way to solve for everything. This way will always work. You don't want to graph before you find all this stuff, so that's why I move it over here. Range is always good to confirm it with the graph. And the other two forms, because sometimes finding the other two forms is not necessary, so you can hold it off until the very end. This way will always make sure you have enough information to do the next step, but sometimes you have enough information to skip steps, but we don't want to kind of mess around with what's working. So hopefully this video is helpful. Make sure you use it to answer the next homework questions, and good luck.